Okay, so guys, today what we're going to do is we're going to take the next step into chapter 4, and we're going to talk about acid-base chemistry. So guys, as we do this, I don't know whether to ask this as a question or to just make it a statement, but the question that I want to ask is, seriously, how you guys doing? I know that you're settling into your classes. I know that you guys have lots of other things going on. I know that you're trying to find the balance in this class. And if you noticed, I really try as much as I can to help you find that balance. How long should homework be taking? How much effort should you be putting into your chapter outlines? Things like that. But guys, I guess I have to ask the question rhetorically when I say, how are you doing? But if you in your head are answering the question, how am I doing? And the answer is, I'm barely hanging on by my fingernails. Guys, understand that the first couple weeks in this class, and things have been a little disjointed because I got sick, but guys, you just got to trust me on this. Probably unlike any other class you have or ever will take at this school, this class is just different. It feels like the safety net is gone. Chemistry used to feel really organized, really accessible, really doable and masterable. And now all of a sudden things start to feel a little loose. Things start to feel a little more undefined. And frankly, for some of you, things are starting to get tense because you're going, oh crap. When you're doing homework, a lot of times you're finding yourself asking the question, how was I supposed to know that? I don't want you to raise your hand, but I suspect that's been the experience for some of you. Guys, here's the thing you got to do. Please trust me. This is not going to come back and crush you. You will find the balance with time. But more importantly, a lot of the experiences that you're having right now that just feel weird are frankly the result of the fact that everything that we've done up until now, with the exception of net ionic equations, has been review. It's everything that you learned last year. And for some of you, it's just not coming back quickly enough. Guys, trust me, we're going to push through this. You're going to be okay. It's not going to kill you or your GPA. We're going to move through this well. And you're going to see, guys, in the next 3 or 4 weeks, you're going to settle into a rhythm in this class, and it really starts to feel different. So if you're having those moments where you're just like, oh my goodness, guys, trust me, things collect and you'll be fine. So guys, with that said, thinking about acids and bases, this is review. So we're going to go through this as if it's review. There are a couple things we're going to need to slow down and talk about. But guys, please, you slow me down as well. Would you do that? If we get into this and we're like, I don't remember conjugate acids and bases well enough, slow me down and we'll spend time and talk more about it. So guys, with that said, let's get started. So guys, and don't write this down, let's set the stage. So guys, when we talk about aqueous chemistry, which is everything that chapter 4 is about, guys, we understand that this is ions and solutions. And you're going to find that there are 3 types of aqueous chemistry that chapter 4 covers. Precipitation reactions and net ionic equations, which we've already done, acid and base reactions, which we're going to do today, redox reactions, which we're going to do next time. Now guys, don't swallow hard when you read this, because that doesn't mean the test is immediately following Friday. There will be another slush day in there where we're going to talk about titrations really quickly, but we are looking at our first test next week. Okay, just keep that in mind. So guys, with that said, today what we're going to do is we are going to dig into acids and bases. So guys, again, please slow me down if you need me to. But guys, let's talk general things that you should understand about acids and bases. Can we all agree on these 2 ideas? That acids ionize an aqueous solution to form hydrogen ions, and when they do, that increases the concentration of hydrogen ion. Can we all get behind that? Now guys, if you can agree with that, let's make sure we're clear on this, because we're going to use the terms interchangeably. Guys, when we talk about hydrogen ions, what are we really talking about? Protons, good. And so if you're not clear on that, that might be worth writing in. But guys, when we talk about hydrogen ions, the things that we're talking about are actually protons. Okay, so guys, with that said, what you're going to find out is that when we talk about acids, there are some new terms that you need to know to describe, and this is new. I'll slow down a little bit. Guys, when we talk about acids, we have what are called monoprotic acids. Monoprotic acids, as the name implies, gives away one hydrogen. An example of this would be something like HCl. The H gives away, the hydrogen comes off, and you end up with H and Cl. So guys, these are called monoprotic acids. A new term for you. So guys, ready for a little head scratcher? How many of the strong acids are monoprotic? Not all of them. All except for which one? Sulfuric, because that's H2SO4. So guys, 6 of the 7 strong acids are monoprotic. Sulfuric acid has 2 hydrogens to give away. That makes sulfuric acid what we call a polyprotic acid. It's an acid that gives away more than 1 hydrogen. So by definition, and I think you probably figured this out, it gives away more than 1 hydrogen in solution. But guys, here's the important thing that you need to know about this. As these things release more hydrogens, their protonations get weaker. They happen less completely. So guys, for example, if you take a look at sulfuric acid. Guys, right below this, if you would please in your notes, write the equation that represents the first protonation of sulfuric acid. Write it down in your notes. Do it as carefully as you possibly can. So you're going to start, if you're not sure what we're saying, guys, do this. So start with H2SO4. When that protonates, what are the products? Be real careful when you do this. Make sure you do it right. Guys, okay? So did you come up with this? So we know that a proton's coming off, so that's H plus, right? But guys, what is our other product? So HSO4, but that's not complete. What's missing? The charge, good. So guys, by the way, I don't know if we talked about this. Do you guys know the name of that ion? Some of you may, because I think we talked about it. So do this. What's that? Sulfate. But it's sulfate with a hydrogen. And guys, it turns out that there's actually a way to do that. If you've got a common ion with a hydrogen on it, add the prefix bi. So this is what is called bisulfate. Exactly. So if you know that carbonate is CO3, bicarbonate is HCO3. This is 2 minus and this is 1 minus. But guys, that's where bicarbonate comes from. The prefix bi means add a hydrogen to it. Now you know. So, guys, once we've got this idea that this is the first protonation. But guys, here's the thing that's interesting. This guy still has another hydrogen to give away. So on the next line, do this. Bring the bisulfate ion down and talk about the products that forms when that falls apart. Like this, we've got HSO4, this falls apart, and we get H plus, and what is our other product? SO4, 2 minus, good. Did you all get that? And do you all understand it's wrong? Why is it wrong? No, the charges are right. Why is it wrong? Okay, so let's do this. Is this a strong acid? Is it one of the big 7? So if it's not a strong acid, it's got to be a weak acids, and weak acids don't fall apart completely. What do? Reach equilibrium. Now it's right. That's a good question. And so, Caleb, the answer is this. This is a strong acid, and then once the first proton comes off completely, let me clean up my mess. So this is a strong acid, and once the first proton comes off completely, this dude, I'm going to call it what it is, the conjugate base, this dude can then release more hydrogens. So it's kind of like strong plus, because it does break apart completely in the first step, and then the thing that's left over can even give away more hydrogens. That's why sulfuric acid is so crazy corrosive, because it actually has a higher molarity of protons than the molarity of the acid. So if you have 10 molar sulfuric acid, you actually probably have somewhere around 12 molar hydrogen ion, because you get 10 molar from the first protonation and probably another 2 molar from the second protonation that isn't complete. Yeah, isn't that interesting? But guys, understand it's only sulfuric acid that does that completely. It's the only polyprotic strong acid. Do you guys get the idea? Okay, so guys, with that said then, let me offer this to you visually, and then we'll talk bases at a theoretical level. So guys, it goes like this.
An acid is a substance that produces hydrogen ions.
Do you find her voice soothing? I don't either. It sort of grates on me, but get used to it. We watch a lot of these videos.
When dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloride.
So guys, what's missing from this picture? They are simply describing the HCl dissolving into water like this, but what really is happening? So if we include water in this, what's the water going to do? It's going to accept the hydrogen and form what? Hydronium ion, but the water molecules are also going to surround the chlorides and keep them dissolved in water. So we would actually form hydronium and chloride ion, but they kept the water out for clarity.
Acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common.
See how it looks like the one from the question in the homework?
Strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong electrolyte. Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it does not completely ionize. It is therefore termed a weak electrolyte.
So guys, it'll come apart, but then what? Go back
or
together.
Weak acid.
And understand, it's not like the hydrogen that goes away goes necessarily back to the same acetate that it left, but it is moving in both directions. Helpful? Get the idea? All right, so guys, a similar conversation with bases. If acids are substances that give away hydrogen, bases are substances that take them in. Acids. We said acids give away hydrogens and they increase the concentration of hydrogen. Duh. Well, guys, it turns out bases take in hydrogens, protons, hydrogen ions, but they increase the concentration of hydroxide. Now guys, this may create tension because you're thinking right now, how does that work? How does accepting hydrogen ions make the OH concentration go up? And the answer is, it depends. It depends on the type of base. So we're going to talk about two different types of bases, and the answer to how does that make the hydroxide concentration go up will be answered differently depending upon the base. So guys, the first type of base that you need to know are the metal hydroxide bases. These things dissociate into solution to release hydroxide. But we have another name for these, don't we? What do we call them? The strong bases, absolutely. These are the strong bases. So guys, obviously, if you've got a substance like sodium hydroxide, you dump it in water, it releases hydroxide. Hydroxide goes up. But then guys, there's a whole nother class of bases that we're going to touch on very superficially right now. These are the non-hydroxide bases. The only one that you need to know, it sounds by heart, I don't know how else to say it, right now is ammonia, NH3. So guys, the question then becomes this: how on earth does NH3 make hydroxide go up? It ain't got any hydroxide. Thoughts? How on earth can this make hydroxide go up if it doesn't have any? That's it. It has to be in water. So guys, you may want to include this off to the side. The non-hydroxide bases can only be basic in water. So the way that it does this, and it's a bullet point, but we'll write it out. Guys, they do this by reacting with water. So let me show you how this works. You've got NH3 and you've got water. Now guys, we've already established that NH3 is a base. So if NH3 is a base, it is going to suck a hydrogen off of the water. And when it does, that forms NH4 plus, which you already know to be called ammonium. But guys, when you suck a hydrogen off of water, what's left? Aha, there's our OH. So guys, the idea here is that the non-hydroxide bases function as bases by stealing a hydrogen from water, and that leaves behind hydroxide. But guys, we still have another problem. This is incorrectly written. Double-headed arrow. This is a weak base. It does not go to completion. It reaches equilibrium. So guys, all of these things do things similar to this, which you already wrote down, and these are the weak bases. Wouldn't you like to see a video? Well, if you don't want to, you're going to have to anyway. Here you go. Karen? Karen? We're calling her Karen. All right, I give you Karen and weak bases.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases.
Now guys, you'll notice, and maybe you didn't like that, they include calcium hydroxide in this list, right? But where do we know calcium to be? Is calcium one of the substances we consider to be a strong base? It is, right? Calcium, strontium, barium, you good on that? Okay, all right, just checking. Here we go. Oh, Karen, come back.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides such as sodium hydroxide, potassium hydroxide, and calcium hydroxide are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base.
Guys, do all of those ideas jive with your understandings? Does that all sit okay? Strong bases, okay.
It is also, of course, a strong electrolyte. Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the ammonium
Yeah? Okay.
and hydroxide ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left.
Oh,
At any given time, most of the ammonia is in a non-ionized form.
so guys, how we doing? Fundamentals of acids and bases. Does that sit okay with you? Okay. So guys, if you're feeling okay about that, what we're going to do now for the rest of the day is we're going to talk about what happens when acids and bases get together. Forgive me, Ken and Caleb, I just need to say this. Guys, we began to look at some of these in lab. So if some of this starts to feel familiar, it is. That was on purpose. But we're gonna dig into this right from the very beginning. So guys, what you're going to find out is there are a series of acid-base reactions that you need to understand. We're going to identify them by the way these things interact. So the first one is what is called the neutralization reaction. So guys, I would definitely make that a heading in your notes. So here's the idea. For the rest of the day, we're going to talk about acid-base reactions. The first one that we're going to talk about is what is called a neutralization reaction. And guys, what we're going to do, and you just got to be comfortable with this, we are going to write the net ionic equations for these reactions. We'll build up to them, but ultimately we need to look at the net ionic equations. So first of all, neutralization reactions. Guys, this is when an acid and a metal hydroxide base react together to form salt and water. And guys, I suspect that some of you see this, but this is a very, very dense sentence. There is so much chemistry contained up inside this sentence. I'd like to spend a second and break it down with you. So guys, when we say metal hydroxide base, what do we mean? Strong base. When we say acid, it could be either one. It could be a strong base. Acid. It could be a strong acid or it could be a weak acid. Here's an important thought. Guys, this is strong, right? Are you comfortable with that? Metal hydroxide bases are strong. That is strong. As a result, this acid could be either strong or weak, and it doesn't matter. This is an interesting principle. A strong base will force a weak acid to completely fall apart. Let me say that again. A strong base will cause a weak acid to completely fall apart because this strong base just beats the bejinkers out of that weak acid and just rips that thing apart. So if you add sodium hydroxide to vinegar, the vinegar gets its butt kicked. The sodium hydroxide just rips that vinegar apart, and the vinegar never gets to reach equilibrium because the sodium hydroxide is a strong base, just rips that weak acid apart. So guys, it doesn't matter if it's a strong or a weak acid. Yeah. It is also true, although for this context, we're not, yes, but you probably won't see examples of it now. But oh my gosh, when we get to chapter 16, it's actually really cool because we actually study how weak equilibria are disrupted by strong things. So we'll look at taking a weak base system and attacking it with a strong acid. And the chemistry is really cool. And then we'll actually go and do it in lab with a pH meter and we really dig into it. But that's not till January. But yeah, absolutely. So guys, this then is the idea. So when we're thinking about these kinds of reactions, we also need to talk about salts, right? Because salt means something to us. Remind yourself, what is a salt? Metal and a non-metal bond together. Now guys, here's the interesting thing. We'll write it down and then we'll think about it. It's a metal and a non-metal bonded together, but guess what? The cation, the metal, always comes from the base. And the anion always comes from an acid. So guys, let me show you an example. Write this down with me. Hydrochloric acid, sodium hydroxide. Simple example, but it's interesting to talk about. So guys, what are our products? Water and table salt. So sodium chloride and water. So guys, this is fundamentally what we're talking about. An acid and a base reacting together to form salt, and in this case I chose table salt, and water. But guys, here's the question. Where does the sodium come from in table salt? Sodium hydroxide. Where does the chloride come from in table salt? Hydrochloric acid. So guys, what you're going to find is that all salts can be related back to an acid-base parent lineage. So for example, sodium chloride, the sodium comes from the base sodium hydroxide, and the chloride comes from the acid hydrochloric acid. And guys, when we get into chapter 16, we are actually going to talk about this parenting idea and talk about the chemistry of these salts. So it's not critical now, but it is an interesting thought that we'll talk about more, that when we talk about salts, the cation can always be tracked back to an acid or to a base, and the anion can always be tracked back to an acid. So, guys, with that said, let's look at another example. Guys, write this down with me big. Here, let's write it down together. So HBr and KOH. Predict the products. Guys, okay? So KBr and can I just put H2O? I'm going to put H2O, but I'm going to write HOH above it just because sometimes it's nice to conceptualize it like that. So guys, did you all come up with this? Are we all okay? Okay. So guys, this is the neutralization reaction that occurs between hydrobromic acid, strong acid, and potassium hydroxide, a strong base. So now here's what I want you to do. Take your writing utensil and kill the spectators. Cross out the spectators. You'll notice that I did not put subscripts on any of these. I'd like you to try to do it without them. This is an interesting exercise. Can we try it? Did hydrogen do chemistry? Started, dissolved in water as an ion. Where did it end up? In water. Bromide, did it do chemistry? Started dissolved in water, ended up dissolved in water. That's a spectator. Did potassium do chemistry? Potassium ion. Started dissolved in water, ended up dissolved in water. Potassium did not do chemistry. Yeah.
I have a question on spectator ions.
Yeah,
So if you
please.
have like those two things that are dissolved in water, so technically they're not like bonded.
Yes.
If they were to evaporate with water, would they bond or would
They do. They reform into salts. Yep. Yeah, and you've seen this simply. Remember the salt and sand lab last year, right? And you dissolve the salt in the water, and then you boiled off the water, and the salt recrystallized. Absolutely. Yeah, they will recrystallize. Yep. Okay, did hydroxide do chemistry? Started dissolved in water, ended up in as water. I like the way you say that, as a water molecule. So guys, killing then our spectators, look what we've got. Hydrogen plus hydroxide yields water. Guys, here's the interesting bit. That will always be the net ionic equation for a neutralization reaction. What do acids do? What do acids do? Give away hydrogens. What do strong bases do? Give away OHs, right? Strong bases. And it's important. When we say neutralization reaction, it has to be a strong base. So acids give away hydrogen, strong bases give away OH, put them together, you get water. That is always the net ionic equation for a strong acid-base for a neutralization reaction. Is that okay? Yeah. So guys, that's the scoop. Yeah. The only time it might be a little different is like, for example, if this was calcium hydroxide, then it would have to balance with a 2. But yeah, other than that, yeah. Huh? Oh yeah. Oh yeah. Unless it doesn't. No, but seriously, guys, but you got to understand it's under the strict definition of neutralization, which is acid and strong base. Then that will be the net ionic equation. Okay? But it doesn't stop there. Another type of equation, another type of acid-base reaction is a reaction involving solid reactants. Doesn't really have a name, but it is important to understand. So, guys, some of your minds are about to go. Ready? So, scratch this down with me. Weird thought coming. You ready? Aluminum hydroxide. Is this a strong base? Well, let's look. Is this a strong base? So it's a process of elimination, right? Our strong bases are our group 1 and heavy group 2 hydroxides, and aluminum is not group 1 or heavy group 2. So asking the question again, is aluminum hydroxide a strong base? No, why not? Because it doesn't, and it does not even dissociate, it doesn't dissolve, right? It doesn't dissolve in water. Are you settled on that? Guys, aluminum hydroxide is not a strong base because it doesn't dissolve in water. If it did dissolve, it would have to dissociate because that's what strong bases do. Guys, this is not a strong base because it doesn't dissolve in water. But you ready for this? It's a really good base. This is an amazingly effective base. This base is more effective than the group 1 or heavy group 2 hydroxides. It is a really, really good base, but it's not a strong base. Do you understand how those two ideas are not contradictory? Guys, what does it mean that it isn't strong? It just doesn't dissolve. Guys, you got to get out of this mindset that strong means good. It doesn't. It just means breaks apart. So guys, this is a really, really good base. It just doesn't dissolve in water. As a matter of fact, it's such a good base that it's the active ingredient in antacid tablets. So if you take a Tums or a Rolaids tablet, you guys understand your stomach's a big bag of hydrochloric acid, right? And if you've got too much of that acid, it hurts. And so if you want to neutralize that acid, you need to get something in your gut that will neutralize that acid. And you'd like that to be something very effective so the tablet's not as big as a hockey puck, right? So you want a really good base. So the base that you use is aluminum hydroxide because you get that down in your gut and there's a ton of hydroxide in there to neutralize the acid. But guys, guess what? You take a Rolaids tablet and throw it in water and it doesn't dissolve. It's not a strong base, but it is a really good base. Are you guys okay with the idea that that's not contradictory? Okay, so the idea then becomes this. If you want to write it down, you can. Guys, just because a substance isn't strong doesn't mean it's not good. This means it doesn't dissolve in water. So let me show you an example. Magnesium hydroxide. Also a really good base. Or would you rather do aluminum hydroxide? Should we do that since we started it? Sure. Let's do that. Aluminum hydroxide. Let's just look at what happens when you choke one of these down. Oh, that's a 3. So guys, when you fire back a Rolaids, it's reacting with the hydrochloric acid in your stomach. So let me ask you this. Is that the right arrow? Does this go to completion? Yeah, because the hydrochloric acid is strong, it does. So it's not an equilibrium process. And then guys, double displacement reaction. Aluminum hooks up with the chlorides, and then the H and the OH makes water. But again, I like to do this just because it helps me balance these things. So guys, let's go ahead and balance this one. So we need a 3 here, and then we need a 3 here, and that balances it. Yeah? No, hold on. Aluminum hydroxide, yes. That's a good question. And the answer is no. There's another name we give it. It's called a non-soluble base. Yeah, yep. Because again, and Robbie, I know, realize that these words, strong and weak, only apply in the context of dissolving and dissociating. So when we say strong and weak, it does neither. In the same way that sand is not a strong electrolyte or a weak electrolyte, it sits at the bottom of the ocean. Same idea. It does neither. Okay, so now guys, I'm going to try this, but this could be a stretch, but let's try this. Let's try to kill the spectators without subscripts. So guys, in order to do this, guys, in your mind's eye, do this with me, please. What does this reaction look like? What does this look like? A powder, literally in a Rolaids, but you could, it's a solid. What does this look like? A liquid, drip, 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 drop, right? Then guys, aluminum chloride, does that dissolve in water? Does aluminum chloride, yeah, it does. Who could it be? Hey, you gonna stay? Please. And then guys, surprisingly, what does water look like? Hey, there you go. Okay, so now guys, let's try to get rid of the spectators without subscripts. So guys, again, in your mind's eye, what does this look like? Part of a powder. What does it look like over here? Dissolved in water. Can you see it? No, it's dissolved in water, right? It's an ion in water. So did aluminum do chemistry? Yes, so don't kill it. So now guys, what about this? Hydroxide ion. What does it look like here? Part of a powder, a solid. What does it look like over here? Water. Did hydroxide do chemistry? It did. Don't kill it. So now guys, what about hydrogen? What does it look like? Ion dissolved in water. What's it look like over here? Water, as you've said well. So guys, did hydrogen do chemistry? Yeah, so we don't get rid of it. What about chloride? What does it look like here? Dissolved in water. What does it look like there? Dissolved in water. Did chloride do chemistry? No, so kill that. So guys, we're going to get rid of chloride, but you'll notice that is now our only spectator. So now when we bring this together, our net ionic equation then looks like, and don't forget charges, looks like this. What do y'all think? Does that sit okay? Now guys, do this with me. Allow your eyes to glance up your page, and let's think about how what you just wrote down is different than the net ionic equation for neutralization. See the difference? What's different in the second reaction than the first? What's the big glaring difference? The aluminum. So guys, the idea is in the first reaction, did we do sodium? The sodium went away because it was dissolved in water first and last. Guys, here the aluminum does not go away because it doesn't start dissolved. So fundamentally, this is the same reaction as neutralization. The difference is that because the base doesn't start dissolved in water, the aluminum is also doing chemistry. Does that sit for you okay? Okay, so guys, we got one more to go. We are going to do this in lab on Friday, and it's nasty and it stinks. Guys, these are what are called gas-forming reactions. There's two types. This is the title, write it down. These are what are called gas-forming reactions. Turns out that if you add an acid to a small select group of salts, you're going to form gases. One of these you're very familiar with. It's the baking soda and vinegar volcano reaction. What's our gas? Carbon dioxide. But guys, the other one we're going to talk about first. This is the formation of sulfides, sulfide gas. If you've ever been to Yellowstone, you've smelled this. This is what is called hydrogen sulfide gas. It smells like rotten eggs when egg guts rot. Hydrogen sulfide gas is a product, so if you ever break a rotten egg, well, that's hydrogen sulfide gas. So how does this formation go? Well, guys, and again, I'll write this big with you, but the idea is this. Hydrochloric acid, again, this is always a reaction with acid, but now we've got this interesting salt dissolved in water, which is sodium sulfide. You'll see it next time in lab. It's this interesting yellow powder. Sulfur tends to be yellow, even in salts. To the end of, did you need to talk with me? Yeah. So I'll be done in like 5. So yeah, please come back. Okay, that sounds great. Okay. So guys, double displacement reaction. The hydrogen is going to hook up with who? The sulfide, the sulfur. So guys, this is going to form H2S. Sulfide is -2, hydrogen's +1. And then guys, again, the Na will hook up with the Cl. And then to balance this, I think we just need a 2 there. Is that right? You okay? You okay? Okay. So now guys, again, let's kill our spectators. Did the hydrogen do chemistry? And guys, let's be clear on this because you don't have context for this yet. So guys, what does H2S look like? Bubbles. This is a gas. Feel free to write it in if that's helpful. This is a noxious brown gas. This is why we're going to do this one in the fume hood on Friday. So guys, it goes like this. Hydrogen starts out dissolved in water. Where does it end up? Yucky gas. Did it do chemistry? Yeah. Chloride started dissolved in water, ended up, okay, get rid of that. Guys, sodium started dissolved in water, ended up dissolved in water, get rid of that. What about sulfide? Did it do chemistry? Started dissolved in water, ended up in yucky gas. So guys, this then is our net ionic equation. that okay? We got one more to go. So guys, that is one type of reaction that forms gases. The other one is the reaction of acid with carbonate or bicarbonate. So guys, let's do this. HCl plus NaHCO3. Bailey, I'm realizing that this is actually an example of the thing that you asked earlier. I'll show you, because the answer is yes to what you said. I said yes, but I said we wouldn't see it. Watch. So, guys, you know what HCl is, right? What's sodium? What's NaHCO3? Sodium, but it's baking soda. Okay, so this is literally dumping baking soda. Does baking soda dissolve in water? Yeah. So this is mixing baking soda water and hydrochloric acid. But guys, is baking soda a strong or weak base? It's weak. It's not group 1 or heavy group 2 hydroxide. This is a base though, but you asked the question, does it work the other way? And the answer is yeah, this strong acid makes this fall apart completely in the same way the other would. So guys, this is a complete reaction. Then double displacement reaction. The Na hooks up with the Cl, and then guys, the H hooks up with the HCO3, this thing again. Aha! And we get H2CO3. But then guys, that's not the end of the story. The H2CO3, which is carbonic acid, then decomposes. This actually breaks apart into carbon dioxide and water. So when you are writing these balanced equations, guys, literally, well, we write it down and then let's talk about it. Guys, what is this going to look like? Well, if you dump hydrochloric acid into baking soda, what are you going to see? Bubbles. And guys, what happens is this. The carbon dioxide is always going away. And as the carbon dioxide goes away, it is not available to react with the water to turn back into carbonic acid. So this never reaches equilibrium because the carbon dioxide is always going away. So as quickly as this is formed, it breaks apart, the carbon dioxide goes away, and the water stays behind. So we will not represent this because it immediately breaks apart. We'll just represent it as carbon dioxide and water. So now let's kill the spectators. Does that sound horrible after a while to say it that way? We'll do this in just a minute. Not yet. So guys, here we go. Did hydrogen do chemistry? Yeah, hydrogen to water. Did chloride do chemistry? It did not. It started chloride and it ended up chloride. Did sodium do chemistry? It did not. Sodium in, sodium out. So guys, our overall reaction is H plus HCO3 minus yields carbon dioxide and water. And that's it. Code. That's a brilliant question. And the answer is, if you were to do the volcano reaction in a balloon, it would actually reach equilibrium. That carbon dioxide would be recaptured, and over time it would actually reach equilibrium, and you would have to represent the H2CO3 because some of it would still be present. I've never seen it. But it's a really interesting question, and you're absolutely right. If the carbon dioxide is not free to leave, it could reestablish the equilibrium with the unprotonated acid. Yeah, that's interesting. You guys settled? Okay, so gang, this then is your homework. There you go. Sorry. So this is it.